So the first topic we're going to talk about in this unit is the idea of emergence, which occurs in complex systems ranging from physics to sociology. So why does the concept of emergence matter? Why include it in this course? Well, I'm going to argue that emergence helps us describe, helps us understand, and helps us marvel at what we see in God's creation. And emergence helps us respond to some reductionist objections to Christianity. And emergence provides an intellectual resource for theology and mission. So this is an outline. First of all, we'll talk about some of the specific reductionist objections to Christianity, particularly ones from the 19th century, but often used today, coming from anthropologists, sociologists, and psychologists. Talk about what is emergence, and then give some specific examples in terms of language, literature, physics, and sociology. And in the next lecture, we'll talk about the role of emergence in theology and mission. So these are some claims you might hear about Christianity, particularly to those who object. One is religion is just a way for societies to be stable. God is just, the humans are nothing but DNA replication machines. Humans are no different from monkeys. Your thoughts and prayers are just the activities of particular neurons in your brain. And so we want to be looking out for these words. Is, only, is just, is nothing but. So let's go to an example. So Richard Dawkins is a prominent atheist, author of The God Delusion, and also has a background in evolutionary biology, and has written some very beautiful books about science, but not so beautiful books about why he's an atheist. And this is a quotation from one of his books, River Out of Eden, A Darwinian View. Dawkins says, in a universe of electrons and selfish genes, blind physical forces, and genetic replication, some people are going to get hurt, other people are going to get lucky, and you won't find any rhyme or reason in it, nor any justice. The universe that we observe has precisely the properties we should expect if there is at bottom no design, no purpose, no evil, and no good, nothing but indifference. This is a very bleak view of life, and which he claims is based in science. But notice the use of the word nothing but. So Dawkins is a reductionist. He's concerned with what you see at the bottom. So reductionism is a process where you break down a system to its constituent parts. For example, you can think about communities, and then you can break that down to think of them in terms of neighbourhoods, but they're composed of families or housing units who are composed of individuals, and then they're composed of brains, and you can keep on going down. And as you break things down, things get a little less complex, and generally the length scales that you're looking at get smaller, and the relevant time scales get smaller. So what is philosophical reductionism? Well, scientific reductionism is a procedure where a scientist attempts to understand a system by determining what parts the system is composed of and what properties those parts hold. So often the focus is on the smallest possible parts. Examples include looking at atoms in chemistry, quarks and leptons in physics, and DNA in biology. But philosophical reductionism is different to scientific reductionism. Philosophical reductionism claims that a system is nothing but its parts, that it is essentially just its parts. And so, for example, Dawkins would claim that a human is just DNA, a DNA replication machine. Now, we're going to see how the concept of emergence undermines philosophical reductionist arguments. So, what is emergence? Well, emergence is one of the most important concepts in the natural sciences and in the social sciences. This is just an example of three books. First one is Social Emergence, Societies as Complex Systems, from Cambridge University Press. And then John Holland is was a great computer scientist, and he wrote this book, Emergence, From Chaos to Order. And then the last one is a popular book by Stephen Johnson about the connected lives of ants, brains, cities, and software. So, what is emergence? Well, the basic idea is that the whole is greater than the sum of the parts. And so we're considering a system of many interacting parts. And emergent properties of the system are qualitatively different from the properties of the parts, or they may not even occur in the parts. So these are examples. Well, I am a person, you are a person, but my DNA is not a person. Water is wet. That's an emergent property, but a single H2O molecule, a water molecule, is not wet. Solid gold, which some Indians love, is very shiny. But a single gold atom is not shiny. Shininess is an emergent property that the whole system has, but the parts do not have. The whole is greater than the sum of the parts. Now, a brain is conscious, but a single neuron is not conscious. We think of a pandemic where COVID-19 is a disease, but a disease is not a pandemic. A pandemic is where it involves spreading to many people. And similarly, SARS-CoV-2 is a virus particle, but that's not a disease. But many of the particles lead to the disease. So a pandemic is an emergent property, a disease is an emergent property. Let's look at another example. Think of language and literature. What we start with is we start with an alphabet in whatever language we're using. And then there are rules of spelling. So letters are combined together to make words. And then words are combined together to make sentences. And that we use grammar defines the rules to make the sentences. And then sentences are composed into paragraphs, and rules of style relate to how you bring those sentences together. And then finally, paragraphs, many paragraphs, can produce a literary genre. According to a literary genre, will produce images and information. And so, as we go up the scale, we there's increasing complexity and there's an increasing number of components. We start with the alphabet. There is only, in English, 26 letters. But from that, we can make many more words. But the complexity increases as we go from, say, all the words in the dictionary into sentences. And the important thing is that at each level, as we look at this hierarchy going up, each level there are distinct rules, distinct interactions, distinct phenomena, distinct concepts, and distinct theories. So if we think about literature, it illustrates characteristics of emergent properties. Because the emergent properties arise, such as a literary genre, or an image, or a paragraph, this arises from simple rules of interaction between the many constituent components. The emergent properties are distinct at each level and are not present at lower levels. At the level of the alphabet, there is no concept such as a word. That's an emergent property. Now, it's difficult to predict what occurs at the higher levels just based on a knowledge of the lower levels. We all know the rules we know the alphabet, and we know spelling rules, and we know grammar rules, but we can't predict or produce from that our own work comparable to Shakespeare or some great novel. There's also something universal, that independent of the details of the constituents from the lower levels, you have things occurring at higher levels. So the idea of an image or a literary genre, that can be independent of the actual language. And linguistics, this is, if you like, a way of understanding some of the universality in language. And so these are some of the characteristics that one sees in emergent properties. First is a novelty, a property that's not present in the individual parts of the system. One also sees a modification of the parts and the properties of the parts and their relationships between the parts of the system. There's also this idea of universality and also irreducibility, the fact that emergent properties can't be reduced to the properties of the parts. The idea of a poem cannot be reduced just down to rules of grammar or spelling or alphabet. And there's this limited predictability. It's difficult to predict what emerges from these interactions just from a knowledge of the properties of the parts. And so emergence leads to a stratification of reality and distinct academic disciplines. And so we can go from starting from physics, from that emerges chemistry, from that biochemistry, biology, psychology, sociology, and so on. And as we go up, there's increasing complexity. Now at each level, there are distinct phenomena, concepts, theories, and techniques. But more is different. And so Phil Anderson was a prominent scientist in my field of condensed matter physics who received the Nobel Prize in physics. And one of the points he made was that the success of methodological micro-reductionism, that's breaking things down to small parts, does not imply a constructivist hypothesis. If we know the laws of one strata, it does not mean we can deduce the laws at the next strata above. Just because we know the laws of physics, we can't deduce the laws of chemistry or the laws of biology, let alone the laws of psychology. So I'll just, in terms of bringing in my own research, I'll just mention briefly how this comes into play. So, condensed matter physics is concerned with this question, and I'll give an example shortly. How do the macroscopic properties of a material, such as hardness, conductivity, color, magnetism, how do those properties emerge from the microscopic components of the material, such as the atoms in the material and their interactions? And here's a concrete example. Consider graphite and diamond. Graphite, like you find in lead pencils, is soft, it's black, it's a moderately good conductor of electricity and heat, and it's relatively common and cheap. In contrast, diamond, like you find in an engagement ring, is hard, it's transparent, it's an electrical insulator, a heat insulator, and it's relatively rare, and so it's quite expensive to buy. Now, the thing is, both these materials are made purely of carbon. They're made of exactly the same components, but they have distinctly different physical properties. And so how does that emerge? And some of the answer relates to the way the atoms interact with one another in crystals of the material. But that's just to give you a flavour of why I'm so interested in this subject, because I've been doing research related to it for more than 30 years. But let's look at an example that now occurs at a much different level, that of society. And so that's the emergence of social segregation. If we look at large cities, we find, in most places in the world, we find that they are diverse with regard to the geographic background, ethnic, economic, cultural, linguistic, and religious backgrounds of the residents of the city. There's a lot of diversity. But if we look at the neighbourhoods in a large city, and also if you look at the churches, they tend to be quite homogeneous. These social units segregate by social status, language, caste, education, wealth, and other things. And so how does this segregation emerge? Obviously, people tend to like being with people like them. But that's actually not true. Many of us would like to live and interact with a more diverse cohort or community, but that doesn't seem to happen. And why is that? And so this is just an example to see how, to the extent that this occurs. This is a map of New York City, and different colours represent different ethnic groups. And you can see how there's very clear division within the city. If you go to Sri Lanka, then you see segregation on religious grounds between Hindus, Buddhists, Muslims, and Christians. Now, if we go to Bengaluru or Bangalore, this is on the left is a map of Bangalore, and then here is a blow up of some of that map down to the level of individual neighbourhoods. Now, what the shading represents is the percentage of people in a particular neighbourhood that are of a scheduled caste or a scheduled tribe. And what you see is this very distinct segregation. So why does this emerge? Well, this is where sociology and a simple mathematical model can provide some important insight. This goes back to Thomas Schelling, who was an economist and sociologist working at Harvard University back in early 1970s. And so he considered this very simple model, and that is where you just take like a checkerboard and then you have two different colours, or you have noughts and crosses that you put on the checkerboard. Now, this is meant to represent a neighbourhood, and each one of these represents a person, say a black person or a white person, or there could be a Hindu or a Muslim, two different categories of people. And then there's some places where no one lives right now. And so each person in the model is only happy if more than a certain fraction of neighbours are like them. And if they are unhappy, they move to a vacant house. So suppose that I want to have at least half my neighbours like me, and then if only a quarter are, then I'll move to another house where that condition can be satisfied. Now, what you might think is you only get segregation if people are very prejudiced, if they really have a strong preference to be with people just like them. But that's not actually what happens, and you can simulate this model on a computer. In fact, you can even download software to do it, this NetLogo. And let me show you what you find. This is what Schelling found. He found that segregated neighbourhoods emerge even when residents have a relatively low preference for neighbours like them. And so here's an example of you start with some random configuration of locations of red people, blue people. They could be Democrat, Republican, or black or white. And suppose that they have a preference that they want at least, as long as 15% of their neighbours are like them, they'll be happy. Well, and you see that there's a little bit of segregation occurring, maybe more than you'd expect. But what's striking is that when you have only a 30% threshold, a 30% preference, that is I'll be happy as long as at least, if you say 1 in 4 of my neighbours are like me, you see that you still get segregation. And when obviously if you have, well not obviously, if you have 75% threshold, you get absolute complete segregation. And so the lesson of this is micro motives don't equal macro behaviour. And Schelling, who later received the Nobel Prize in Economics for other work, wrote this book, Micro Motives and Macro Behaviour. But there's tipping points where at a certain level of tolerance for neighbours, you get the change. So this is just an example where social sciences can give you some insights, but also you see the concept of emergence, that you start with a system which doesn't favour, on the scale of the individual component, does not favour segregation, but nevertheless segregation emerges. And so a lesson from this is if we want diverse neighbourhoods, we're going to have to work hard at it. So let me summarise. Emergence is one of the most important concepts in the natural and social sciences. The whole is greater than the sum of the parts. And we'll see, pick in the next lecture, how emergence helps us to respond to reductionist objections to Christianity. And we've looked at various examples of emergence. And we'll also see in the next lecture how emergence is relevant to theology and mission.